For the next test, we're going to perform an AC input failure and recovery on the UPS system. So we're going to be operating the UPS at 50% load. So we have the UPS input, going to converter out to the output, batteries available, operating at 50% load. Then we're going to transition the UPS to an input failure mode where the input will be open from the main switchgear. So the UPS will be forced to go onto battery operation to provide power to the load. It'll run for a period of time. We'll close the AC input breaker back in, and then the UPS will reassume the converter operation, walk in the load to the converter, and slowly walk off the battery, and then provide pure UPS power out to the load the entire time. So now we're going to begin that test. So you can see we open the AC input source, which is also our bypass source in this operation. The contactor opened, the converter stopped. We closed the source back in. The converter restarted, and the whole time the UPS output never changed. So let's go out to our data acquisition system and take a look at how it performed on a very close examination. So here is our data acquisition report of our input failure and recovery test. So here's the output voltage during the entire event, and then our utility input current to the UPS. So here's the power coming into the UPS. The power is removed. The UPS is forced to go on battery the whole time. AC input actually closes back in right here. The UPS looks at the input, determines, is this input good or is it still transitioning? Do I need to stay on battery a little bit longer? Once the input is determined good, which the UPS then turns on the converter and walks in the input and then goes back on full standard operation. The interesting thing about this is all of these time periods are adjustable. From the time period, once AC input returns, the amount of time the UPS utilizes to determine is the input source good can be set from anywhere from 0 to 3,600 seconds. The walk-in period that the UPS walks back on, so you can set it 0 up to 3,600 seconds. So changing the ramp and the time. The reason for that is if you have a nice long battery source, you want the input to the UPS to be very stable before you transition back off of batteries. But if you have a flywheel application you're looking at, you don't have a whole lot of time to have the UPS be pulling power from the batteries. Every second counts. So you could shorten this entire window to being just 1 second of checking the UPS, their utility, to see if it's good, and then the walk-in being very slow or very fast on a flywheel application. Another interesting point is if you have natural gas generators, you can, instead of the diesel generators, you can actually extend the walk-in to a much longer period of time, and that generator has lots of time to slowly ramp up operation before the UPS puts all the load onto it. So let's take a look a little bit closer at these transition points on this. So we're going to look at the input transition from input power to battery and how that affects the output load to the UPS. So here's your output voltage. Here's your input current. The input current goes away, the UPS transitions to its internal battery source, and the output voltage maintains very stable operation. So you can see at this transition point, there's very minimal deviation on the output of the system to the point of 0.48% max deviation. So less than 1% deviation in this transition event. So let's zoom back out and let's take a look at this ramping function of the UPS. So here, the UPS turned on its input contactor. The input filter caps become charging and discharging. We turn on the converter. The converter then minimizes that current to those filter caps and then begins walking in the UPS in a nice slow and steady ramp up to full load of the UPS at that point in time. The time period on this is currently set at 10 seconds for full load. Since we were at 50% load on the UPS, well, this actually will run for exactly 5 seconds until it's fully loaded at that low point of the UPS. The output voltage remained stable the whole time, but one thing I do want to point out is the interesting thing here of how as we're ramping in, your output or your input caps on the UPS, your DC link, your caps that are operating the DC link of the UPS at 750 volts DC. As you ramp that converter section in, those capacitors get higher and higher voltage to make this ramp nice and steady. So once you get to the point where you're at the full load, we need to discharge those caps back down to ensure a nice stable output voltage waveform. So as we ramp in, we're ramping in nice and smooth. We discharge the DC caps a little bit internally, and then we go right back on smooth operation. But as you can see, the voltage waveform to your load never deviates more than the 0.48% that we mentioned earlier during this entire operation. So let's zoom back out. So as we went from input current failure to the current being turned back on, the converter starting and ramping back in the load, that entire operation, the output voltage waveform maintained within 0.48% total deviation, so nice and smooth operation. We really appreciate you watching this video, and if there's any questions, feel free to reach out to us and we can provide more detailed discussion on any of the topics you saw today.